Okay, good afternoon everybody. Great pleasure to be here. Thank you very much to the organisers for the invitation. What I'd like to do this afternoon is to tell you a little bit about some of the work that I've been involved with, and perhaps share with you a bit of a vision of what I think precision farming may be in the future. My role as a research professor is to look ahead, to look forward, look over the horizon a little bit more. So some of the ideas that I'll be presenting to you today might seem to be very novel, but I'd like to think that most of them are also reasonably practical, and I do expect that we will have a number of these different technologies appearing on commercial farms before too long. So for those who haven't come across Harper Adams, we're a university in Shropshire. We've got some fairly good student satisfaction and teaching excellence and employment statistics. This is the department that I'm head of. We have 2 degrees, agriculture engineering and off-road vehicle design. These are both unique in the country. Offer a whole range of different degrees, from foundations up to PhD, and lots of buildings and vehicles and staff and so on. We are going to start a new Masters in Precision Farming later on this year at different levels with certificates, diplomas, and going up to Masters. And another one in applied mechatronic engineering. We're developing our work with China and Brazil, and with lots of companies. Of relevance to this group, last year we set up the National Centre for Precision Farming. We have actually managed to raise £3 million. £1.5 million was raised privately, and another £1.5 million came from the government Catalyst Fund. And the graphic of the building that you can see in the background there now is actually, the steels are up and it's growing day by day. So we should have an opening ceremony later on this year. So the centre is being set up to be an inclusive, non-competitive networking hub used for passing on information and bringing people together. And so we're having discussions with a whole range of different companies and farmers to be able to bring or find some sort of central repository for all of this information. And we'll be setting up short courses and technical days and conferences and events and so on. And we're trying to see if we can make the whole concept self-funding, in terms of then adding value to those members. So a little bit about some of the work that I was doing before I started at Harper Adams. I was managing the European Futureform project, and part of that remit was to develop smarter machines. And we can see a whole range of strange-looking machines that have been developed doing different things around Europe. But if we look at what's going on in current agriculture, we can see that machines are getting bigger all the time. There's some very good reasons that these machines are getting bigger. Current systems are very effective, reducing labour costs per hectare, high work rates, good for large farms and fields. And this effectively is all coming down to economies of scale. If you're going to pay somebody to sit on a tractor for an hour, it's better that they can do 20 hectares rather than 10 hectares. But there are also problems with it, in terms of that you're still having to pay somebody to go onto the vehicle. It's high capital expense to be able to buy one of these new vehicles, reduced flexibility, it's non-scalable. And we've got particularly issues with compaction and trafficability. And I'll come back to that point in a moment. Now, one of the fundamental aspects of precision farming is about management units and the reduction of scale of the management units. So perhaps traditionally we would manage the whole farm in one way, or perhaps the whole field in one way. Precision farming, we've seen that it's better to divide the field up and treat what is needed in the particular places and at the particular time. But if we extend that into the ultimate goal, then in fact we can come right the way down to the opportunity of managing each individual plant. Now that might seem a bit strange if you hadn't thought about this before, but I'll give you a number of opportunities where we are actually now doing this. So we've got the opportunity to be able to manage at different scales. To be able to take advantage of these opportunities, we don't just need to come up with a new gizmo, a new black box, a new screen, and plug it into an existing system and hope that it's then going to make money or be useful to a farmer. We actually need to consider the system itself and how best to modify it. And what I'm starting to develop now is a whole range of smarter machines, particularly smaller smarter machines, that is based on plant needs rather than based on how we've done it in the past. And we can then maybe start to do operations we cannot do now with current equipment, or find too expensive or time consuming. Where we're dealing with low energy, intelligently targeted inputs, if I try to summarize the aim of what I'm trying to do in all of the research is, what is the minimum amount of energy that we put into the natural environment to turn it into agriculture? What's the smallest amount of energy in all its different forms, whether that's tractors, diesels, chemical, whatever? What's the smallest amount of energy to turn the natural environment into something useful for us? And at the moment, we see that we throw energy at the natural environment a lot more than we should. And there are significant savings. I'll show you some examples in a moment. So we can come down to small area or plant scale operations, very low compactions, modular and scalable, cost effective, and of course management is a fundamental part to all of this. So as we try and design this new system, we think about the machine or perhaps the robot that's going to be in the middle of it, and we need to think about safety, energy, economics, environment, management, mechanization, technology, and society. This is the systems approach where we then have to recognize that there are multiple perspectives and we have to respect those. And of course it then starts to become very complex very quickly. But if we are going to try and develop something inside this area in the middle here, we have to take into account all of these different factors. So the system's implications, if we try to do this, will be minimal energy inputs, which then will be good for environment. Allow controlled biodiversity. Perhaps that's something that we don't normally think of. If a plant, we like to have a monoculture, we like to have our crop plants out there in the field. But if you're getting other plants in there that are not competitive, then they're not a weed, they're not a problem, they're not causing us a problem. So perhaps we've got the ability to retain non-competitive weeds. Of course, economics is important, labor costs, incremental investments, scalability of these different things, social opportunities. So there's a whole range of different things that we can bring into this mix. But I'd like to explore this concept of energy with you for a moment. If we've got our farm, where does the energy come from? Well, of course, all energy comes originally from the sun. And then it comes indirectly then onto the farm through light, air and rain and the weather and temperature and so on. But that energy has been stored up in the fossil fuels, and we then introduce energy in terms of the chemicals and the herbicides and pesticides that we introduce to the crop. We also then use energy through fossil fuels to build the tractors and to be able then to apply fertilizer and so on with our machines. And of course then the output is the food that we then desire. But there are other implications from that, and that is that some of this energy then is coming in terms of off-farm pollution, in terms of waste, and the biomass that perhaps we don't normally then use. Well, we've been talking a lot recently about all the different energy crops, and of course we can then have a closed-loop system where perhaps we can then have energy crops that can come back and be able to fuel the vehicles. The government won't like this because if you're growing the energy crop on the farm and using it on the farm, there's no way that they can understand that you're being taxed or that they can't tax you on it. But we thought we were pretty clever when we came up with the idea, but as often with new ideas, we find that these are not new ideas because years ago this was the horse and we would grow grass and then we would feed the horse on the grass, and so there's nothing new under the sun here. So the concept is that what we want to do is to control these inputs to be able to control the outputs. And this is where we're dealing with this concept of intelligent placement of energy. And so that, so that we can then restrict or only put the minimum amount in here, we can then minimize the wastes and so on. And one of the things that has come up in many years of looking at precision farming, it's very rare that we ever manage to actually increase yields. What we can do with precision farming is two things. One is that we can reduce the cost of production, so we can reduce the inputs for the same yield. And the other thing that we can do is to control quality. And so if you don't have a quality aspect on the crops that you grow, there's limited use for some of the precision farming operations. So we're talking about robotic agriculture, multiple small machines replacing large man tractors. We've got to make them safe and reliable, easy to manage, incremental costs, and design these new systems to allow us to do what we want to do. But what effectively I'm doing here is trying to take away the machine limitations. And the more I think about this, the more I realize that the machine limitations we've got at the moment are actually significant problems. So if they're lightweight, able to work in soft soils, small, autonomous, dealing with the weather independence, weather dependence, and a whole range of different factors associated with these smarter machines. We can actually make some significant savings, whether it's a manned tractor or an unmanned tractor, in terms of what I call spatial control of machines. And so we've seen the advent of RTK and a lot of auto steer systems where we're using the AB lines and the parallel tracking. But that is only the first step. The next logical step then is, rather than AB lines, is to have complete route planning. And I've had a number of student projects working on this recently where we're coming up with odd-shaped fields and then working out different techniques to be able then to come up with optimal route plan to allow us then to have this concept, this spatial control of machinery. We've seen how important it is to make sure we don't have any skips and overlaps, but also in which way we work the field. So again, I make no apology for complexity. Everybody in this room is used to dealing with complexity. The natural environment is complex, and we have to find ways of dealing with that complexity. And part of that new development is to come up with systems that are sophisticated enough to be able to deal with that complexity, but hopefully can simplify it so we as mere mortals can deal with that level of complexity. And so we're currently working on a number of different subsystems within this to allow us to come up with a management information system to be able then to make use of these smarter, more independent technologies. I talked about route planning. I have a website, webfarming.com, that started to develop under the Futureform project. And this is Harper Adams down here, and here's the engineering section. This is the engineering field here. And this is Google Earth plugin. And you can click around the outside here, and you can then tell it what tractor you've got and you're working with, and it can then come up with an optimized route plan for you. So it's a little bit more than craft knowledge. You can change the directions to see whether it will work or not, and you can actually then get a feel to see whether it's worth doing. And again, we can often see between 10–15% savings by choosing the correct direction of working. The next stage, once we've got these route plans, is to be able then to not only use it this year, but use it next year. And of course, if we're then going back on the same tracks over and over again, we're then into controlled traffic farming. Now, a few years ago, I remember being at one of the HGCA conferences, and a farmer stood up and said to everybody, if you're not doing auto steer, then you need to do auto steer. It's a no-brainer. And everybody started thinking about it. If a farmer says this is a no-brainer, then everybody thinks, right, well, maybe I need to think about it. Well, the next no-brainer is controlled traffic farming, in my view. And the ability then to be able to keep our machines, big machines particularly, onto particular route plans, and then not cause all of this compaction is a significant step forward. I love that picture. I like big tractors. I'm an engineer. Put me on a big tractor, black smoke coming out, great, I love it. There's a big but here somewhere. I had a group of Swedish farmers come and visit me a couple of months ago, and they, in the sort of broken English, said, we have got a problem this year. It's a wet year. Yes, we all know it's a wet year. And they said it's the wrong sort of weather. And that sort of clicked in my... Where did we hear that not long ago? What about the wrong sort of snow? Do you remember that on the railways? They would blame the snow, not the train. And it just suddenly registered with me that, in fact, it's not the weather that's wrong. We can't control the weather. It's the tractor that's wrong. Why have you not been able to put seed into the ground when you want to put seed into the ground? It's not the weather. It's not the weather's fault. We don't have a tractor that can do it. This is a seminal moment for me. We've got to change what we do. And in fact, what I realized is that the bigger the machine, the smaller the working window that we've got. And the smaller the working window we've got, we need a bigger machine. This is a self-fulfilling prophecy. So that as the machines get bigger, the working windows get smaller, and so the machines have got to get bigger. We've got to think about something in a different way. So current tractors cannot enter the fields when the soil is wet. And okay, we've got a nice tractor there with lots of horsepower, but horsepower doesn't help when weight is the problem. We need the weight to drag things through the soil, and the weight is causing the problem. So can we design a tractor that can run on wet soil? Here's an old slide used by Dick Godwin for many years. I credit him because he's dug the hole and had a look at the soil pan in here. But when you think about it, why do we cultivate? Okay, we can say we need to break the soil up and all the rest of it. Large tractors cause significant soil compaction that results in up to 90% of the energy being used in cultivation to repair the damage caused by the machinery in the first place. Up to 90% of the energy that you're putting in cultivation is there to get rid of the damage that the machines have caused in the first place. Again, we need to think about this. Low ground pressure tyres, controlled traffic farming. Can we develop a system that does what we want without causing compaction problems? Ultralight machines, micro-tillage, zero draft force. There's a whole range of opportunities. These little red robots you might have seen in the press, I use them a lot. I developed them with AGCO and a design company. This is not meant to say this is what's going to happen. These are discussion documents. If we were to develop smaller machines to do something useful for us, they've got to have certain characteristics. And it's at that stage that we're at now, trying to work out, well, actually, how big should this machine be? And what should the ground pressure be? Well, certain parts of this we can understand now, that the pressure underneath the tyres should be no more than 40 kilopascals, so that we don't damage the soil. And if we can get to that sort of stage, then we can start making all sorts of changes. Stop dragging heavy bits of metal through the soil. Can we do things like micro-tillage and so on? Which brings us on to this concept then of plant-level husbandry, or phytotechnology, as my Japanese friends call it. And we can break the cropping cycle down into the three levels of three areas: establishment, crop care, and then selective harvesting. So we're coming up, when we're dealing with this, we're coming up with new terminology. So we're talking about things like seed maps. So we've got the ability now to be able to record every seed that goes into the ground and its position. We've then got the crop map, or the emergence map, where it has then come out. We've then got the ability to record patches of weeds, or where individual weeds are. We then need to understand the difference of treating the weeds in the inter-row area, which is different from the intra-row area, so the area inside that row. And the most critical of all is what we now call the close-to-crop area, where it's within the canopy, within the biomass of the plant. And we've then got to be very, very careful about what we do in that area so we don't damage the plants. So for seeding, again, we heard previous speakers this morning talking about problems of germination and establishment. Even the seeders themselves will produce void areas. When we look at it at the seed level, even when we get ultra-high accuracy seeders, they still will miss seeds. And these then are potential areas where we've got voids and hence no production. We've got problems of competition. When we put seeds too close together, they compete with each other. What we really want to try and do is to find the optimal placement for each of the seeds and make sure that each one grows properly. Can we develop the concept of a reseeder? There is no reseeder on the market at the moment. If you've got an area that once that perhaps was wet and is now dry, or didn't get the right establishment, can we come up with a machine that can then go out and reseed or transplant? Can we control seed of depth of the seeds for moisture? It's drier on the top, it's wetter further down, so adjust the depth. Can we orient seeds to reduce competition? So here's the seed mapping machine, standard high precision seeder with an RTK GPS and some little electronics in there, and with a light beam, as the seed drops through it, it cuts the light beam and we can record the position. We can go out and take some images of it and overlay the data. So the red crosses are the GPS, the blue cross is the position of the aerial, the red cross is where we think that we've dropped the seed, and we can go back out there and actually see whether we've got seeds or emergent plants in that position. And usually we can, and it's usually to within 2 centimetres, the same level of accuracy that we get with the GPS. But of course we can get errors not only from the GPS but also from the soil aggregates. So if we wanted to be able to put seeds exactly where we need them, why do we put them in rows where we have all of these problems? Well, the main reason we put them in rows is that it makes it easier for the machine. But surely we should be beyond that now. If we want to have seeds in optimal positions, we should be able to develop a machine to do this. And so perhaps we would then think that we need an equal area for each plant. But immediately you can see that we're getting lines here in exactly the same way, but in a different direction. So that doesn't necessarily then help. But we can then perhaps consider, well, why don't we use grid seeding? And if we've then got the ability to be able to put seeds into the ground in terms of synchronized planting, that will allow us to give this optimal area for each of the plants. And if we've then got the random weeds coming into the system, then perhaps we can utilize orthogonal inter-row mechanical weeding, so that weeder doesn't need to be a smart weeder. We can just go in two directions. And again, we thought we were pretty clever chaps until I talked to an old farmer, and he said, yes, we used to do that with horses. And of course, it was done with horses, and they had a rope down the field with knots in, and every time it hit the knot, the seeder would drop the seeds, and then they'd move that across to the next one and come back. So what they were doing with ropes, we now have to have RTK GPS to do the same thing. But nevertheless, there is some very good reasons for doing it this way, and the high technology can help us if we want to. We've got the area of where we're looking at plant breeding and looking at the phenotypes of plants and so on, and which actually is a very expensive and very time-consuming area of agriculture. And of course, people have to do that. Well, we are now coming up with new machines that can do this for us automatically. So crop scouting is laborious, low levels of repeatability, weather dependent, and so on. And here are some of the robots, or this is one of the robots that we were playing with 10 years ago when I was in Denmark. Got lots of different sensors on this machine, laser sensors, cameras, RTK GPS, and we've got a downward pointing camera on here to be able then to look at the crop row through here, and to be able to identify individual seedlings as we come through. Not only can we identify the seedlings to see whether they've germinated or not, but we can also then recognize the leaves and, in fact, the meristems, the growing points. And I'll come back to how we can use that in a moment. So this was the first generation of Crop Scout robot that was developed in Denmark. Four-wheel drive, four-wheel steer. I say this is robotics. It's not rocket science, it's robotics. It's not, that's just good engineering. That's just very, very straightforward. There's no more cleverness going in that than even the simplest tractor. It's just motors and gearboxes. The cleverness actually ends up inside the computer. So that was developed. That was the first generation. The second generation is the Bonnie-Rob robot developed at Fachhochschule Osnabrück with Amazon. A lot of hydraulics on there, nicely engineered, very capable machine. And it's got a lot of sensors underneath there, the light curtain and multispectral cameras, being able to understand a little bit more about the plant automatically. And in fact, then we're now looking at the third generation of vehicle that will be able to do this in exactly the same way. And this is what I'd like to develop in the UK. I need to talk to TSB in a little bit more detail to make sure that we can get some funding to be able to do this. So with the scouting system, we have the weed and crop mapping with machine vision, crop stress through ethylene detection, insect infestation through volatile organic compounds, crop growth rates through crop height, nutrient status, crop quality. So there's a whole range of these different factors that we can put onto these machines that are non-contact solid state sensing systems. There's a little video here. Hopefully it'll run. The blue lines are where the lasers, the range-finding lasers, will go onto the Bonnie-Rob, and from that we can then be able to look at the plants themselves and to be able to understand many of the actual physical characteristics of the plant. I do a lot of work in China. I have some visiting chairs there, and it is amazing how quickly they are developing. Normally, in previous years, I've been going to China, helping them. Last year I went there, they were telling me new stuff that I'd never heard of before. And one of the things that I liked very much was the concept of 3D canopy models to give us context. If you've got a sensing system and you go and take one reading, what you have is your number, 56. But what you don't have is the context of that reading. What was the plant? Where was it taken? What was going on? What part of the leaf did you take it? And if we've then got many, many readings, as we can then have with these more automatic systems, we can actually then develop full 3D models automatically of the canopy. So not only do we then have a reading on that one leaf, but we also know what leaf it was and what the plant growth stage was and what the species was and so on. So its context is an important part of making these machines more intelligent. I talked of weather-dependent spraying and weather-independent spraying. At the moment, if perhaps there's too much wind and it's a manned machine, it goes out in the morning, the wind gets up, right, we then go home. If we had an unmanned machine, we should then be able to get it to sit there, wait for the wind to drop, and if it only drops for 10 minutes, at least it can continue for 10 minutes. So we can actually start expanding the workability windows that we've got by having more of these smarter machines. I showed you the video earlier about lots of little plants going past. Well, what we can do is use machine vision to be able to recognize up to 26 different species of weeds. And we can see here, here's a picture of the panchromatic picture. We've then got a template on here, and by how that template is modified to fit onto the leaf is then going to give us an indication to which species that is. So we can then identify each of these weeds, how big they are, where they are, and so on. We started with the concept of microspraying. Again, this is about 10 years old, where we don't have weeds around here. We've dealt with them through mechanical ways, but perhaps we were in this close to crop area and we've got weeds that are really close here. And we can then perhaps have a camera and a little inkjet, like an inkjet printer, to go across and to spray over each of those weeds. And what we can see down here, here's the robot itself, and down there is the, is it not running, that one? Okay, so this robot's moving a fair slowly, and there's a camera underneath, and there's some leaves on the ground, and it's then just putting some chemicals over each of those leaves, which then can save us from 720 grams per hectare down to 1 gram per hectare with that machine. Now, this is a video of a PhD student who's just finishing his work. He's a PhD student of one of my old PhD students. You probably can't hear the commentary, so I'll explain it to you. So this is a lab test of a MicroDot sprayer. And so what we've got here is a hood that then will go over the crop row. There is a camera on the top there. We've got artificial lighting inside there. And underneath there, the black thing is 7 jets of what's called a microsprayer. So it's like a mini spray boom across there. And the idea is that as the plant goes past, the machine vision can then recognize the weed and then will apply the chemical only onto the leaf of the weed. So, okay, we're using a robotic arm. It's just because we're doing it in the laboratory. So we're moving the plant past the camera rather than the camera moving past the plant, but it's the same principle. The camera in the laptop then is doing the analysis. And if you look onto the leaf of the weed, can you see some blue spray on there? And that's then saving 99.99% by volume. That to me is one of the best examples that I know of a smart machine. So rather than having to have the chemical choosing which plant it's going to attack, we can use the machine to say attack that plant and do not attack that plant. And so we've got the ability to be able to differentiate and to treat at that level. Mechanical weeding by hand, very expensive. Somebody was telling me the other day, I don't know whether this is true, £1,000 an acre for mechanical weeding. A lot of money. There should be better ways of doing it than this. We developed a Cycloid weed hoe to be able to do the inter-row and intra-row area. And we've now got another video that doesn't work. And this one is of my autonomous tractor running through the field, and the Cycloid weed hoe is avoiding all the lettuce plants. So it's weeding between the row and inside the row and leaving the plants behind. Okay, and so if we took that same idea, we could then put it into the robot. And the other concept is this concept of laser weeding. And what we can then do is to have a laser with a steerable mirror on here to be able then to just heat up the meristem of the weeds. It's not Star Wars, it's not lightsabers, it's just a concentrated heat source. And we just heat up the meristems to within 56 to 94 degrees C to get the cells to rupture. And that's what it can do in reality. Again, in the laboratory. So this is not commercial, but we are working on it. We've got the opportunity now to be able to, and you notice that these plants are still green. We're not killing the whole thing. What many of them do is just go dormant. So the plants still remain there, but they are non-competitive. So it's not a problem for us. We've got a whole range of other little robots and machines that we've been developing. Here is a Christmas tree weeder that I developed in Denmark. Christmas trees are an agricultural crop, not a forestry crop. And another video that isn't working down here showing the machine actually running through the field. And another video that's not working. We were very honored to have Professor Noboru Noguchi here from Hokkaido University. I managed to get him across here on a Royal Academy of Engineering Distinguished Fellowship program. He is I think he's the world leader in agricultural robots, and he's just done some tests of this tractor cultivating at night. So he's showing that the machine can actually work over the whole night. We're now getting into the phase where we're looking at much longer term tests for these machines. We've got a new project just starting under ICT Agri, and at Harper Adams we'll be developing an autonomous orchard robot with a perception head on the front here to allow it to navigate through trees, but the idea of having it navigating through trees is to carry a whole range of different sensors. Selective harvesting, again, is a very expensive operation. Even though we try to utilize cheap labor, it still is expensive, difficult to support large labor force in terms of houses, buses, transport, and so on. Whole crop harvested and graded, up to 60% of non-saleable quality. Can we design a selective harvester that only harvests crop of 100%? So if Tesco's wants lettuces this big, or Waitrose wants onions of that big, not bigger or smaller, can we come up with a system that can only harvest those things? And this is the concept of selective harvesting. So we can actually then look at what's going on in front here and only select those and harvest those plants or parts of the plant that can be harvested directly. And on the back here then is just a trailer. But we're leaving behind perhaps the smaller ones. We know how big they are, and we know that in 1 week's time they'll be the right size, so it might make sense to come back and harvest them in a week's time. So in conclusion, it's obvious that farm equipment is going to become smarter. We're going to have improved automatic control of well-defined tasks, automated data gathering, better processing into real information with the possibility of fully autonomous vehicles with sensible behavior in given contexts within the next 5 to 10 years. And I think we now have the chance to develop a complete new mechanization system that meets all of the requirements of modern agriculture, taking advantage of all of the technologies that are now on offer. Thank you very much for your attention.